All right, ready? Welcome to the afternoon session. My name is Helen He. I think on agenda, we'll be talking about OpenMP, right? And then followed by OpenMP and hybrid, OpenMP and MPI hybrid. Then we have some break and go on with interactive hands-on sessions for the afternoon. If you have still need to catch up for the morning sessions, don't worry, we have time to do that as well. So about OpenMP, I'm gonna talk about the concept and things, the major components of OpenMP, directives, its data scope, runtime libraries, runtime routines, and how to use OpenMP. Then some little bit concept of hybrid programming. We are open about OpenMP. The history, it started in 1997 when, major industry compiler vendors having started to diverged into using multi-threaded programming in their compilers. So a group got together, so let's try to create a standard. So that's how it started. There's now an architecture review board with 30 plus members, and LBL/NERSC is one of the members. I am a representative in this language committee that representing NERSC users and to try to get new features and try to, let the OpenMP, the specifications have our users' needs in mind. So the current standard was 6.0, which just released in November by the Supercomputing time. And things 4.0, there are old. So we are going to talk about only the CPU side of OpenMP, but it's basically we call them OpenMP Common Core. But things OpenMP also can be used for GPU offloading. So what can OpenMP do? OpenMP is a program for, as Charles mentioned in architecture today, is for multi-processing shared memory language. It's like if you have the nowadays architectures, you have many nodes for the supercomputer, and on each of the nodes has lots of CPUs or physical cores, and usually on the same node, all these cores have a main shared memory. They may have cache levels, and they are not shared, but the main memory on each node is shared. So it's easy to have to do the MPI explicit send and receive. It's more like cumbersome to program. So we could take advantage of shared memory on the node to use this OpenMP programming model. So the way to do that is like you will add lots of so-called compiler directives, and a compiler can choose to ignore it, treat it still as a sequential code, or add some kind of special compiler flags so that these directives will be recognized by a compiler and then use the multiple threads to parallelize these code. Because of this feature, the code is relatively easy to maintain a single source code for your serial code and parallel code. Also, you can parallelize proportionally or progressively. You can find a hotspot in your serial code and then just only parallelize, speed up that portion. And when that one is becomes less a hotspot, and then work on the next computational intensive region. So that's the advantages. There are, as I mentioned, the API is basically called Application Programmer Interface. OpenMP is also a runtime library. Then you can compile with when you compile, you would use the structures defined, and then the libraries defined in the API. So there are directives, compiler directives. There are some libraries you can call at runtime. There are environment variables you can set. And then with those environment variables, you don't have to change your source code. You don't have to recompile your application. You can just change the environment variable and say, for example, it's a different number of threads to use for the same executable. there are three categories of these API functions. Some of them would control your parallelism, we call them flow control, like where do I start, how do I parallelize them, where do I merge them again, where's a barrier, all sorts of things. There's also a communication part of the API. For example, different multiple threads, they could hold a shared memory, like everybody has the same value of a variable, or they can even have their private variables. The way of OpenMP works actually is there are lots of private variables that each thread work on its own part of data. But at some point, there's a communication, meaning they talk to each other, or one thread put data there and the other thread could read it. So that's how they share to the communication. They are sort of different from MPI communication. MPI communication, you would send explicit data message to the other MPI rank. For OpenMP, there's a shared memory. One thread put data there, and in the memory location, when other thread access that location, they sort of getting this variable values with maybe we call this implicit communication, right? And there's also synchronization. Similarly, OpenMP also has a barrier, and there was some different programming scope. There's implicit rules of when a barrier, there's explicit barrier, you can call OMP barrier. There are implicit barriers, and once, different terror regions, when you end a terror region, there's an explicit barrier. I'll talk some of these into details. So OpenMP again is shared memory, basic parallelism. The way it is called a fork join model, the master thread. The name is now deprecated starting 6.0. It's using primary thread. A primary thread is like in a sequential region, there's only one thread word process. This thread doing lots of sequential process. And then at one point it says, I want to fork many threads to do the parallel work. So now it enters into a parallel region. And when this region is done, all the threads join. Basically, you will leave only the primary thread. The primary thread can again do some sequential work and then fork another parallel region. The second parallel region can use different number of threads than the first one. It can also fork a parallel region within a parallel region, which is a nested parallel region. So it's fork and join, fork and join. That's the programming model of OpenMP. Now let's talk about directives. Go over the syntax and then different types of parallelization, just basic parallel. A region, inside parallel region, every thread will do the same work. And then there's a work sharing loop. It's like if there's a loop, I definitely don't want every thread to do the whole loop. So there'll be work sharing. Each thread will be responsible for a part of the iteration space. The different kind of schedules. How do I distribute my work? Usually it's schedule is on top of the work sharing loop. How do I schedule? Like I split them evenly, or I do them some kind of smarter ways to distribute work. That's called schedule. And then synchronization, as I mentioned, barrier and other ways. Then reduction. And you've heard of reduction in MPI. There's similar concept in OpenMP reduction. There's another thing called YMP loop. It's also a work sharing loop, but a different way of specifying the loop to distribute work. The syntax, the C, C++, and Fortran. In C, C++ is # pragma, OMP, and a directive name, and some optional clauses. # pragma is a Greek word, but I think it's distribute work, sharing, teamwork thing, than OMP. And then it basically follows standard rules for C++ compiler directives. But this special directive, as I mentioned, if you don't put a compiler flag to enable OpenMP, it'll be ignored. So this is special pragma or OpenMP directive. There's a new line, you can do it. It's Greek for saying done. Let's do it. C++, again, C is case sensitive, right? And then when you have this directive and then you have a scope for it, if there's only one line the next thing you want to be part of this OpenMP, region, you don't have to do anything. But if you have multiple lines, you would do a curly braces, just to put the things you want into this parallel region, or into this OpenMP region. Doesn't have, without a parallel keyword, it's not even a parallel region yet. Right. For Fortran, there are 3 ways accepted. It's called sentinels. So there's like, from now on, we kind of recommend to use only one way, because the other 2 only works for fixed format Fortran. But for the free, sorry, the for the other 2 only applies for fixed format, right? And the pound dollar OMP, it's called Sentinel. It works for both fixed and free form Fortran. Again, it's standard rules apply for those, and then there's special rules of between with fixed and free. There's like, where is the continuation line should be? For fixed, it's like line 6 or some column 6, all these, and where's the where can you put starting of these containers? A free form is more free, but then and you have to, if you have a continuation line, you have to end the first line. It was a ampersand, and the next line would again was a sentinel, and then to continue for your directive. We're not talking about actual OpenMP region. It's just the directive sometimes is way too long. You have to have a continuation line. So here is an example, right? For C, we mentioned it's a curly braces too. So parallel is basically, once you have this keyword, it's parallel is a directive. If you have parallel, then the region, the scope is in parallel. Basically, it's executed by multiple threads. If there's not a loop, then every single thread will run the same thing. And these are some private as the scope. I'll talk about scope a little bit later. And then shared is also a scope. There's also can be sometimes a schedule, also different type of clauses can follow behind this directive. For Fortran, you have to have a start and end, just the OMP parallel and then OMP end parallel, right? Because there's no curly braces. Here's a simple example here. You would include OMP.h for C. For Fortran, you use OMP. That's a module. Then in Prava, OMP parallel. In this example, I'm not setting how many threads are going to run it. I'll tell you how a thread is determined, the multiple ways to determine that. Assuming when I enter the parallel, there are multiple threads executing this. And in this example, I'm actually using an OMP runtime library call, which is OMP get thread num. It's very similar to get MPI rank. I get my personal thread num. It also starts from 0 to number of threads minus 1. So each thread will run this line, and I'll get its personal individual ID, thread ID, TID, right? And then I'll print it. So, this line, everybody just printf is before entering parallel. So only the thread 0, it's primary 0, and we'll exit this line. They'll print this line only once. And inside it, every thread will print its own thread number. And once it's exited, that's only, again, the primary thread will print I am sequential now. So if you run it, as a Fortran example, Fortran example is very similar as OMP parallel and then OMP end parallel. Again, each thread will get its OMP get thread num. So when you run it, it's like from output 1 would say hello world from threads 1 2 0 0 1 2 3 4. I'm sequential now. Run it again. There's no predetermined ordering. Each thread running parallel, so it very much like you can get the out of order output, right? Different threads because they run totally completely in parallel. And the execution is scheduled by OS. Which thread is, some thread is busy doing work slower, faster. Some thread is even responsible for OS work, IO work. Really depends. So now I want to talk about work sharing loop. So the beauty of this, you see in previous example, each thread have just printed its own thread ID. But the idea is like, say, if I have a big loop and I have many threads, it's good for them to distribute work. For this to do is to basically, in C syntax, a loop is for I equals 1, 0 to n, and minus 1 or C starts with 0. Then so OMP has a keyword directive, it's OMP4. You just add that with different schedule or something. I'll talk about schedule a little bit later. And private meaning some data within this OMP region will be private to each thread. By default, they are shared, meaning each thread have the same value. And the schedule is a way to how I distribute this for loop. In Fortran, very similar, but in Fortran, loops are do loops, right? That's the almost the only one that the keyword, the directive are different. Is different for C and Fortran. All the other directives are the same in OpenMP. And you also have a schedule, you have this the scope thing, and then OMP and do. Your OMP do, OMP and do. Usually this thing is embraced in a bigger OMP parallel region. So in the real code, you would pound $OMP parallel, and then followed by OMP do schedule and OMP and do. So I'm going to talk about static, different type of the schedule here. Notice there's also a no wait. No wait meaning by default, each thread will wait for each other, wait until the whole loop finish. But if you add a no wait, meaning if one thread finishes sooner, it can continue to do work on the next command. For C as well, C no wait is up in the top because there's the end OMP thing. So it's there. For Fortran, no wait is on the end line. So static. Now let's talk about scheduling. What does there are ways of distributing, right? So static meaning the distribution of or the partition of the iteration space is determined at compile time because you know how long is your loop. It has to be pre-known, compile time known, the loop length, so that, and you also know how many threads. So static without a chunk. So you see there's a optional chunk. Without a chunk, the way it does is basically divide by the number of the iteration space divided by the number of threads. So say if I have 100, the total length is 100, I have 4 threads, each one will do 25, 25, 25, 25. But I can also give it a chunk. If my chunk is 5, for example, then I'll do 5, 5, 5, 5, the first 4 threads, come back to the first threads, to the next 5, next 5, next 5, right? This you can give a chunk as well. But everything is determined at compile time. So at runtime, it's relatively faster. But the overhead is low. The problem is sometimes your work is not even. Even your loop seems even, but the work, for example, your a matrix is not lots of zeros in a matrix. Sometimes some loop will finish much faster. So with the static scheduling, it could cause lots of load imbalance, meaning one thread finishes much faster, waiting for other threads to finish. So then we have this dynamic scheduling helps with what it does is by default, its chunk is 1. So each thread would do the first iteration. So if there's I just 0 to 99. I have 4 threads. The first thread will do 0, the second thread will do 1, the third will do 2, the fourth will do 3. And then the first thread comes, whoever finishes fast, doesn't mean the first thread will always finish. Whoever finishes fast, pick the next iteration, then come back to do number 4, and then whoever finished, come back to do number 5. So it's like very fine-tuned, the chunk of 1, but then you can do a little bit bigger chunk. You can make each chunk, say 5, then the first thread with the first 5, second thread with the second 5, and whoever finishes first to take the next 5, because it's dynamic, right? Then the whole distribution is determined at runtime, because it really depends on runtime who finishes fast, who finishes slower. So with dynamic, it takes longer time at runtime to do all this, management, who finishes this and that. But overall, it also helps the load balancing because whoever finish faster will do more work, and then they'll all threads will finish about the same time. There's also another thing called guided. The reason is with dynamic, it helps with load balancing, but the chunk size is pretty fixed. So if the chunk is too small, it takes too much overhead managing them. And at the end, if all of your chunk is too big, there still can be potential load imbalance. With guided, it does is a chunk size decrease at iterations. First, at the beginning, chunk size is a little bigger. So it has a little less overhead. But then when it's closer to the end, makes the chunk size smaller and smaller so that it be fine-tuned to do load balancing. So guided schedule is sort of take the best from both static and dynamic. However, it's not standard OpenMP standards in the specification, so not all compilers have it. So there's another thing, an option called runtime. Basically, you just let the compiler choose whatever it thinks best for you. You don't decide what to do. It's all the chunk size, how it changes, or how they distribute. It's all decided by the runtime. So these are the options for the. Let's go back to see this line. Basically, you have all important OpenMP schedule, and then you have the type of scheduler type here and the chunk size. Okay. So if I have a loop, how do I know if my loop is parallelizable? First of all, I said you need to know number of iterations it needs to know. Otherwise, and it can't change. If it's changing, say for example, you have linked list, you don't know how long it's going to be. When you don't know when it's going to stop the loop, or if there's a while loop, these kind of things you cannot parallelize with easily. There's OpenMP tasking. We're not covered today. It's a tasking way of parallelizing. It's doable. But when we do the do loop or for loop here, if you don't know the number of iterations beforehand, you cannot parallelize them with these simple ways. Also, since we are now letting different threads do different part of work, they have to be independently done. They cannot be the one iteration dependent on previous iteration, because you have to do them completely out of order, and so each iteration has to be independent of each other. So if there's data dependence, you cannot parallelize those. There's also like C in C++, there's iterator loops, those cannot be parallelizable. A quicker way is not always correct, but if you run the loop backwards and you give you different results, they're definitely not parallelizable. If you do it backwards but you still get same results, likely it's parallelizable. Meaning they are there's no data dependence. Here is an example, Gaussian elimination. You know what is Gaussian elimination? Sort of like you try to solve matrix question, A times X equals B, right? And this A is like, usually you would write them in a matrix format. And then you have all the components, all the coefficients in this matrix. And then the way to do it is do the pivoting. You have first line equation, second line equation, and keep the first line there. And then from second line on, what you want to do is sort of here, using this as a matrix example here. Is the first, each line is an equation. And we start from this corner, it's an I loop, I equals 0 to the end of the matrix size. And treat each of them as a matrix, as an equation. You want all the values in each matrix grid here are the coefficients, right? And what you do is you time this whole equation by a factor, so that the number of the value here times this new value equals to the value there. Then you subtract the second equation from the first equation, so that you make this value to be 0. And the same thing, you do the next line, to the next line. Every single line equation times a different coefficient, a factor, so that they now all match the same value of the first equation here, and you subtract each line from the first line, you make them all 0. Now you have a smaller size of matrix. You do it again, now I equals 1, you do it again. And then you make all these 0, all the way down to the end. Then you solve things backward. Once you have the last line, only one value, so like 5x equals 10, and then x equals 2. And you put that x2 backwards to then the next one, earlier had 2 unknowns there. Now you have 1 known, and then put the known value there, and then solve the next, unknown. So that way it is like, when you go from I equals 1 all the way down there, the next value, how there's a little in a square that is like 1 dimension less on the I dimension, it has to do in the order of I equals 1, then you make it smaller, I equals 2, and then make smaller, I equals 3. You treat them smaller and smaller. So on I side, it actually, the next step of I has totally dependence of the previous I. So basically in the previous loop, what I'm saying that I loop is not parallelizable because there's data dependence. But look at the J and K. Let's say this column wise is J and row wise is K. What I'm doing is, once you time this equation, a coefficient, when you start to do the minus, you're doing them grid by grid. And there's no issue if you do a different grid first. Just doing subtraction from the first line. So the J and K, there's like basically you can do them in any order. So that means that J and K can be parallelized. So here's the our code here. We know that when you parallelize them, you basically add OMP parallel and then OMP parallel 4, right? So we need to add progma OMP parallel 4. You can actually combine the parallel and the 4 into one line. So we're adding progma OMP parallel 4. We know we cannot add it here because it's not parallelizable. So we could add it either in front of 4 for J loop or in front of the K loop. Where do you think is best to put there? In front of J or in front of K? Or we can do both J and K, right? The problem is that if you do it, say that the answer is you put it outside of J. You wanted to parallelize outer loop. As Rebecca mentioned, something coarse grain, fine grain. This is like sort of more coarse grain. Because if you do it in front of K there, then for every J loop, you have to, there's an overhead to fork an OpenMP region. Meaning, there's also some data management there, there's multiple threads, and then later on you have to, join the threads. So you don't want to do it every single time each J, especially if, the K loop doesn't have, the iteration space is small. You have too many fork and join. So it's better to do it out there. Then for each J, all the K loop will be all, they'll be like basically divided the J loop there, and then the whole loop of K will be done by a single thread that's responsible for a part of the J loop. So if, say, I have, in this example, it's a square, so the iteration for J and K are the same, right? What if, my K loop is much bigger than J? Then if my J loop is very narrow, then I have multiple threads there. That's not a good distribution for OpenMP. So one of the optimization is that we could do a loop exchange. We can put K outside the loop. There's no issue there. Just switch the order of them. Then you put the OpenMP still out in for the outer loop. One thing I didn't mention earlier, there's actually another clause. We could collapse this loop, meaning the compiler sees this collapse. We could put a progma OMP on 4 and collapse parentheses 2, meaning I want the compiler to treat these two loops as one. So internally, compiler will make a new one-dimensional loop, then I'm distributing my one-dimensional loop by number of threads here. That's actually more efficient. So sometimes when the loops are totally independent and multiple loops, I can collapse them. So this is an example here. Outer loop I is not dependable of each other. We cannot. Inner loops, yes, in any order. I already explained these. So this is the right way, OMP parallel 4, right? I mentioned earlier parallel and another loop, another line is OMP. The first line is OMP program OMP parallel. The second line is program OMP 4, but you can combine. This is just for your convenience. It's completely equivalent of have them separate lines and with the curly braces to put them together. All right, collapse, I didn't put it here, but you can just type here, collapse, parentheses 2. Okay, now, synchronization. There are implicit synchronizations, but sometimes, just like OpenMPI, when you don't send and receive, at one point, you want everybody to reach the same place that my send and receive are complete. OpenMP is similar. I've been doing some of the. One example is that this loop, right? What if I have some other computation followed by this computation? I want to use the result from the above. I do want the first part to complete. In this kind of loop, there are implicit, we call synchronization there. You don't have to, but some of them don't. For example, I'm going to talk about a single. Some single meaning one thread does it, and then when this thread does it, by default, there's no wait. Other thread doing something. But if you want other thread to wait for this single thread to finish, you have to have an explicit barrier there. I think critical is one of the barrier. Meaning, what does critical mean? Meaning, only one thread can do it at a time, but all threads have to do it. One example in the Dart example, when you accumulate the number of darts, right? So I throw a dart. I'm within this, circle. I want my overall darts count to add by 1. So each thread can come in. I throw something. I got my results. And when I add, my result is I'm within the circle. I want my numbers of counts to add by 1. I need to do, all threads have to do it, whether I add or not, but they have to do it one at a time. So that's a critical section. So OMP is critical. And for Fortran, you'd end on and critical. Then single. So you can do OMP single, OMP and single. And then single is useful for, if, say, I want only one thread to write something to do, especially for the things that we call them thread unsafe, meaning thread unsafe meaning OpenMP has lots of implicit memory model that and from time to time with a synchronization, it allows you to have some in between different. It's like there are a value of a variable can be different depending on where you are. When you are within a parallel region, but before you do the barrier or synchronization, it can have different values. The I/O is also kind of special that we call it thread unsafe. So it's best to do just by one thread. Or say you write thing to a memory location. If multiple threads write to it at the same time, you may have overwritten issues that we call it data race, and you will have wrong result. But anyhow, I/O is totally recommended to do it by one thread. So usually do single because you don't care which thread, right? You can say OMP. In the past, there's a directive called OMP master, meaning thread 0 to write. Master is deprecated, and now it's OMP masked, MASKED, still meaning thread 0 to write it. But single meaning one thread to write it, it can be any thread, doesn't have to be to the thread 0 to write it. And then this barrier is no other directives, no other clause, no other anything, just OMP barrier, meaning everybody has to reach this, then go on. Very much like MPI barrier. Okay. A reduction. Again, similar to an MPI example. So for example, in the darts example, now instead of the critical section, what I can let OpenMP compiler to handle is that I would put my OMP, the count plus lines inside a reductions region. What it does is, usually it's also a loop. So multiple threads will have a partition of that loop. So let's say the summation, right? What I do is my one thread will do a local summation of this loop that is assigned to my thread. My next thread have another partition of the loop. I'll do its local summation. And at the end, compiler will help you to do a global summation. Basically, it adds each local summation. But without this reduction, again, without reduction, without critical section, whether you do a local summation or a global summation, each thread will try to write the same memory location. And whoever writes first will be basically overwritten by the next thread. So the reduction underneath is sort of, depending on your implementation, is likely one of the example algorithm would be some sort of tree algorithm. So like a little partition, a local summation is everybody writes to the thread 0 in this local group. Another local summation partition section right to the first location, and then sort of like 2 to 1, 2 to 1, 2 to 1, sort of down to the final output. This operation here can be plus meaning summation, and time meaning products, multiplication. There are lots of logical operations here, the max numbers, mean numbers as well, all these. So there's also, when you do this, there's we call them a base number. So for summation, the base would be 0, right? And then you have local summation, add them together. Finally, add all them together, add on to this base 0, get your final result. For the multiplication, the base should be 1 because you have a local product, all times them together times the base number, which is 1. Can be 0 again. If you 0, your final will be 0. So MP reduction is sort of function-wise is MPI reduce function, but it's also just a directive to write. It's pretty simple. The final directive is called loop. Again, the loop is also within OMP parallel. And then instead of OMP4, which is more, you tell compiler how with the OMP4 to distribute your loop here, basically it's a loop for a loop. You would tell compiler how I want my scheduler is, how my chunk size or my, for OMP loop is basically, hey, compiler, you decide what you want. Can help me to do distribute my loop. So the way we call this OMP loop is a more descriptive way of distributing my loop, distributing my work. And OMP4, OMP2 for Fortran are prescriptive way of OpenMP. OpenMP is mostly prescriptive. You tell compiler what to do. Until recently, we added OMP loop. It was added in OpenMP 5.0. And it's like mimic what we had in OpenACC. But OMP loop works for both CPU and GPU. OpenACC mostly for GPU. It does work for CPU as well. But the purpose of OpenMP is starting from OpenMP on the CPUs, and then we have them on GPU as well. The OpenACC started from the purpose of make them work on GPU first. So here is the directive within OMP parallel again, and then you have the OMP loop. Then again, you give them the scope here, the private and shared. I think have not talked about scope yet. I will. Next. Loop gives you the freedom for pairwise. And then again, you can all these similar to loop for OMP and do, OMP for functions and do, there's no weight. For C is OMP4, and you can put the no weight on the top. Now, scope. Any questions? Should I check? Looks like Rebecca, Justin answered lots of questions in the Q&A, so I don't have to do it. Okay, if you have questions, you can put it into the Q&A. We have so many people answering. Charles, Rebecca, Justin are all online. What happened? Scope. Okay, what does scope mean? So in a parallel region, the variable can be private and shared. Let's use an example. So say it's the index, no, loop index, right? For so if you have a loop inside the parallel region for I equals 0 to n-1, and each thread may be working on different I index. So this I, you can imagine this should be private, meaning each thread will have its local memory to handle what this I should be for the special, for this certain thread. But if this say all the threads working on big matrix and they each work on a small part of the matrix, the whole matrix can actually still be shared, especially if you are reading only, not even modifying it. This matrix can be shared. So shared and private, this is what it means. And by default, all variables are shared except loop index. And you don't even have to specify it's private. OpenMP does it for you, but it only does the outer loop. So if we have multiple loops, nested loops, and you have only one OpenMP region, the only outer index is default. The inner indexes are still shared. So you have to specify those are private, because the inner, if you're nested loops, the inner thread, each thread will be working on different inner thread as well. So you have to make sure those indexes are private. And the local variables, if you decide, if those are even declared inside the parallel region or inside the subroutines within parallel region, they are private. There's also declared, we call them lexical extent. So lexical extent meaning there's a region and you call some function. The functions called within the region are outside of lexical scope, meaning the lexical extent meaning the compiler can decide, can work out the actual declaration, the actual private sharedness of these variables, then they're within the lexical extent. So variables declared within those the lexical extent of parallel region, they are also private. The scope is the most common source of errors. OpenMP looks simple, but if the scope is wrong, there's also very hard to debug. You get a result, how do you know? I know it's the same. A few ways to check it is though, if you run with 2 threads, 4 threads, if the results are different, likely they're wrong. If you're running with multiple threads and results different from 0 run, likely wrong, right? But the scope is so important. So one thing we actually wanted to do is to use a default, the default. So by default it's shared, right? But usually we want you to say default none to force you to have to think about each variable, whether they are private or shared. And then you put shared, which variable is shared, which variables are private explicitly. That'll help you to debug. Otherwise you would have like silent race conditions. It's just hard. Besides private, there are something called first private and last private. What does it mean? Is that if you say it's private, when you end, if you have on your directive line, you said private of this variable, or you've declared a variable inside the parallel region, they are basically, if it's just private, they are undefined. When you enter into the parallel region, there's no value. The first private meaning if this variable is declared before you enter the parallel region, it has a value. Then you will enter in the parallel region, it basically already defined and has that value inherited from before the entering. So that's called first private. Last private meaning within the parallel region, you do something, you have this variable defined as some value. When you exit the parallel region, the variable value will have the last, basically usually it's last loop index, the value that you have it for that variable. So common mistakes, I mentioned about explicitly declare all variable scope. Race condition, overwriting. There are a few tools that actually help you to scope. There's a create review, there's Cody. We have had training materials, honors training like this one. It's recorded, and later on you'll find slides and videos on our event website. Similarly, like the tools I mentioned here, we also have slides and videos on our training website. You'll find them. These tools, because especially for more complicated applications, it's really hard to scope every variable. And not just one single sort of file. Your file can be your application can span across many files, different definitions, subroutines calls. So sometimes those tools can help you to scope these variables. So here is a Gaussian iteration code here. Programmable OMP parallel 4, right? Find the mistakes here. The hint is that we should, give it scope, things like that. Anybody can spot any issues here in this example? What about J? The J's private is shared. So if I have multiple threads, I'm going to each thread work on a little partition of this J loop. Each J would be private for the thread. So I should put private J here. Although it's redundant because the compiler will do it for you because it's the first loop index, right? What about K? By default, K will be shared, but obviously this K, is part of the J loop here, and then each thread may be working on different K at any moment. So you would have to put K as private here. What about this big A matrix? A can be shared, the A big matrix. But ratio here, because it's just a scalar variable, and it's by default it's also shared, but different J, different I, and you override the ratio a lot, right? So here, K and ratio are shared, but for K, sometimes compilers are smarter enough because it noticed it's also an index loop, loop index. Even though OpenMP compiler specification does not give you this as private, but some compilers may be able to find it and optimize it and put private for you. But the ratio is definitely an issue, right? Because it's a variable, and whenever each thread working on this getting a new ratio, it's being overwritten. So definitely you have to put ratio as a private. You put J here is still fine, but the I is totally for each I you're doing more OpenMP. So each I within this parallel region is shared. So like I said, put a noun here, that will force you, if you forget one variable, the compiler say, hey, you forgot to declare it. The B here is never, the bigger shared big matrix, and each thread is only writing in a different location at a time, so that's okay to be shared. Big N is never changed, so those are shared. Those scope wise, you cannot just write your code like this, it'll get you wrong result. Okay. Yeah. Okay.
Could you explain what specifically would be happening there that you're going to get the wrong result? I guess I'm not entirely following this argument or this situation.
Sure. So let's just use the biggest issue here is the ratio, right? So let's say that we have two threads here. One thread is working on j equals I. The other thread is working on j equals I plus 1. And then depending on who does it first. So the first thread does it first, it has its ratio. But then the ratio will be used later for this thread, let's say thread 0 and thread 1, right? Thread 0 will use this ratio. But what if thread 1 finishes later for the first line? Thread 1 will have its ratio, override the ratio to be used by thread 0 later. So whoever the thread, I want this ratio to have different value for my thread 0 and thread 1. So if it's private, it'll have its different value in a different local memory for each thread. But if I don't put it in the private, by default it's shared, meaning when thread 0 modify its ratio, thread 1 will get the same value that modified by thread 1. Although I should have my thread 0 ratio to be used thread 0.
So it won't create a copy then and just pull it into, and if you moved your declaration of ratio to where you're assigning ratio, would that mean that you're then essentially creating a new double within the scope of each thread and that they would therefore be independent?
You are correct.
Okay.
So if you say int ratio is that the things like I mentioned, the things declared, where do I have the by default, very local variables, within subroutine call are private. Variables declared within external pararegion are private. So, like you said, if I define my int ratio here, int ratio, then it becomes private. But my ratio is defined here above pararegion, so that's shared by default. Did I explain?
And is there no way to do like an atomic index? Oh no, because it's a single, because ratio is a single floating or double value and you're looking up where that value is. I see. Okay. Thank you.
There are people padding this, make ratio as an array or something, right? Then you could say ratio of my TID, and then each ratio have only modifying the TID's value of that ratio. Then this ratio can be shared, just like A and A here, because you're modifying memory location of this big array here.
Mm.
But if it's a scalar, then it has to be private.
Perfect. Thank you.
Okay. Runtime libraries. There are a few things here. I was mentioning, how do I know how many threads my code is going to run? There's one library that OMP set num threads and give a number of threads. So if I call this thing before entering a pararegion, then basically whatever number you set, number of threads total I'm going to use is for the next pararegion to use. So this thing you have to call it outside the pararegion. And if you don't call it again, if you don't change it again, or if you don't set it in a different way, it'll be used for the next pararegion. And even if you merge them, join them, and then one more pararegion, it still uses the same value, unless you change it in some way. And then within the parent region, you can call get number of threads, and I'll tell you how many threads you have. If you call get number of threads outside the region, you get always one. And you can, if you set inside the parent region, it doesn't affect how many threads you use within this region, because it has to be set before entering this region. So if you do call set number of threads, it'll affect a nested region inside a parent region, the number of threads to be used. And get thread num is getting my local thread ID, sort of get MPI rank. This is like get my ID. So inside this parent region, if there are 4 threads, my thread num may be 0, 1, or 2, or 3. Okay. So these are the most important runtime variables so far. And then environment variables, you can set them at runtime. So if you say, I set export OMP num threads equals 4, and you have compiled your OpenMP code, and you run it. You set this first, and you run executable. It'll use 4. And you change this number. You set OMP num thread export OMP num threads equals 16, and you run the same executable. That executable will use 16 threads. Similarly, there's a schedule you can set. Schedule, we were talking about static, dynamic, and a chunk size. So these are the type and the chunk size, the way you can also set an environment variable here. So if I come back, there are actually 4 ways of setting number of threads and in the order of precedence. So how compiler would decide. First of all, I didn't mention, I mentioned some kind of clause, right? So there's actually a clause you can use. So you can actually put it in the parent region here, number of threads, how many. This will be the highest precedence. If this is set, however other ways you use, it'll use the way you set here in the clause. So you can set a clause here, and then when you get thread num, it's my local thread. And if you get number of threads, it'll tell you it's 4 inside here. The second one is that, like I said, this is also used, you set it before entering the parent region. Then it'll use 4 here. This is on the condition if you didn't use the clause. If you use the clause, even if you set it, it won't affect. The clause takes its highest priority. The second highest priority is that you set it there. The third one is you do it at runtime, export environment variable. So if you set this, you change this. However, if you have this set number of threads in your source code, your export won't take effect because this set number of threads is higher precedence than number of threads environment variable. And the fourth way is you do nothing, then compiler and operating system will decide how many threads it'll use. Nowadays, I think most compilers use however many threads you have. So if you do on the logging node, we have 256. If you don't set anything, your source code don't do any of 1 or 2 here. Runtime, you don't export, it'll run so many threads you have on your logging node or on the computer. In the past, when at least I know one of compilers always use default as 1, but now more and more using however available to you. Sometimes, however many, sometimes your OS system or even your sysadmin can set. One user can always only use this max, even if your whole logging node has like on a shared logging node, 256. Your system admin can set it. Everybody can use max 8 or something. Depends. So that is when you don't do any settings. So we usually do the most flexible way is the OMP number threads value, environment value. Then you don't call set number thread. You don't put in number threads in the class. Just set OMP number threads in environment variable, and you can change from run to run. It's very flexible, actually. That's probably my favorite way. The number 3 is my favorite way. But the other 2 is usually when you want to have reproducible results, you want to have the production ones, and you want to share with others, you may want to do the other way. One almost last few things I want to mention is so this actually what do we call it? macro is defined in OpenMP specification underscore OpenMP. The way to do this is like, if your source code has something OpenMP functions called, and you compile without an OpenMP flag. I think, right, did I mention this thing? I want to tell you this. So compiler flags, if you want, you have you have OpenMP runtime libraries in your source code, you have to compile with this, especially with the source runtime libraries. If in the directives, it's there. If you don't compile with flag, it's fine, it's just ignored. But if you have API runtime calls there and you forgot to use the flag to compile, it will complain because I don't recognize your runtime library. So the way to do this is also one quick way to do this is the macro. You say, if I have, OpenMP defined, I want you to include OMP.h. Otherwise, even if I called this function net, if I have OpenMP defined, it'll recognize this way. But if I don't have OpenMP, I don't want this source code to compile to generate an error, I can define my own, runtime function. Just define this as 0. Then in the case that I don't have OpenMP, I will return 0 and without a compilation error. Probably don't use that much, but it's just in case you have OpenMPs. But there, one way to work around this is you always include OMP.h and you always compile with OpenMP. But that also would backfire because sometimes you don't want to turn on OpenMP, you want just run with one thread. So that's why the macro is useful in those situations. But come back to the directives, the compiler, Pragma, OMP, or Sentinels. The purpose actually to turn on OpenMP, right, with those directives. You put on those, you want to turn on OpenMP. So then don't forget to use these compiler flags. On our parameter, GNU compiler is the default. So to turn on -f OpenMP. And we also use Cray compiler is -f OpenMP, and the NVIDIA compiler is -mp to turn on OpenMP so that you can run with multiple threads and see, speed up. You might not see speed up for the Dart exercises running multiple threads because the overhead of OpenMP or even MPI are pretty high because your application is too small. But for the real large applications, when you run with multiple threads, when you run with multiple MPI ranks, you should see speed up. I mentioned when you run this, usually for OpenMP, I don't think I want to talk too much about details here, but there's something we should consider, something about affinity, meaning you have to basically put your OMP threads onto the available underneath CPUs that in a smart way so that they don't overlap on each other, meaning you make some cores work too hard, like multiple threads on the same core, and then other cores or MPI ranks are idle, and also to consider some sort of memory, bandwidth type of things. We have a JavaScript generator, especially when you run hybrid MPI or MP. In this example here, this is a standard way of setting here. SRAW-N8, meaning you're running 8 MPI tasks, and each MPI task is here. I will run 4 OpenMP threads. Rebecca's going to talk more about hybrid MPI and OpenMP. The reason is this: in huge, big applications, you would run on multiple nodes. Then once you're on multiple nodes, you cannot just use OpenMP because they are not shared memory anymore. You have to do explicit memory message passing MPI to share to distribute your work. But once then on each once you have multiple nodes, then use OpenMPI across those nodes. But on these nodes, you still have so many cores that you can use MPI as well, but many times you want to use OpenMP on those nodes. So that makes you using MPI and OpenMP hybrid. Then when you do that, in this example, I'm using 8 this example actually using only one node here because I can tell by n times and 8 times actually 64 is 512. That's parameter CPU node has a total of 512 CPU cores, logical CPU core. Then with 8 MPI tasks, you're still having lots of CPUs available that you can use OpenMP. You can use up to 64 OpenMP threads here in this example. Then we have some default ways of where you want to put your OpenMP threads at. It's called OMP places, meaning each thread, setting this to threads, you can set it to cores. Setting it to threads, meaning each little thread can be independent OpenMP, thread that has its local memory, has its ways of managing its local work for each thread. OMP proc bind, meaning I want my threads to a little bit apart, don't step on each other, and number of threads. So with these variable settings, it's probably hard. I'm not trying to explain this here in much details, but when you run MPI, when the hybrid code, I think it's also one of the hands-on exercises here. We have a script generator, and you put in how many MPI tasks we want to use, how many threads we want to use. It'll spit out the settings like this for you. And just concept is we call this affinity process, and thread affinity is very, very critical. Without setting these things, you might exact same source code, exact same binary, you might get suboptimal performance. I think that's that. The next exercise would be computing pi with OpenMP. So we mentioned you have C codes and Fortran code. Don't take anything from MPI, just take it as sequential code as your start point. And use shared memory parallelism to compute pi. Notice there's a loop, you have to update the count of the darts sitting within the circle. And think about, should I use loop? Should I use, critical section? Should I use reduce? Should I care about my scope, variable scope? These kind of things. But it's relatively simple. You probably only need to change 1 or 2 lines of code and verify your results with running multiple threads compared with sequential code. You should get similar results. If it's wrong, it'll be quite wrong. Yep. Yeah, and slides are already uploaded on the Q&A doc. So you can get to this exercise. I think the idea is we probably want to go on with the talk and then come back with the both of the slides, right? I see Q&A docs are answered really well. So thank you for helping answering the questions.
You don't mind just looking at the one about
Just
first private. I answered it, but
yeah.
you have a better answer.
First private. Why first private is last private needed? So first private meaning you can bring in some values already and already, have defined and calculated, then you can bring it in and use it in your power region. But each of them, that's still private inside the power region, but it's just each private region will have this value as their initial value. Instead of it has 0, you have to recalculate it, right? Last private is similar. You have this thing calculated, and then you can have it, just bring it out to the after power region and use that value in your next step of the workflow.